Good afternoon to you all. So we were discussing about ideal gas law and ideal gas equation in the last class. So in this session also we are back with another law, which is Dalton's law of partial pressure. We will see what is partial pressure and we will find out what is Dalton's law. So when we spoke about pressure of gas, we had told how it is actually induced. So pressure of gas is the product when gas particles move inside a container and they hit the walls of the container, and that will form the pressure of gas that we had discussed earlier. So now in this case of partial pressure, we are considering not just one gas, we are considering different kind of gases in different vessels. So one category is this. So we can consider this as gas A. So next we will consider gas B with different condition, not different condition but different gas in different vessels. So we are considering three gases in three different vessels here. All of these gases are different. So gas A is different from B, it is different from C, and their pressures also will be different. So as the particle is different, they will have different type of movement and different type of hitting in the vessels. So because of that, they will have different pressures also. Gas A will have a pressure of P1, gas B will induce a pressure of P2 in this vessel, gas C will induce pressure of P3 in this vessel. So all of them are different gases inducing different kind of pressures. And one more important factor is they are not reacting to each other. If we mix up in a same container, they should be non-reactive also. So in this condition, Dalton stated his law. So we are taking all those gases in a same container. To a bigger container, we are transferring all these gases together. And the condition is constant temperature and volume is provided. How much ever we are taken there, so that the same volume is taken here, and with the same temperature, that also in non-reactive condition. All these gases should not react to each other. For example, nitrogen and helium, like they are not reacting to each other. Similarly, these gases should not react with each other. If they react with each other, the partial pressure or the pressure will be different. So now we will see what happens. This all will move in the container, and this also will induce a pressure inside, right? So as we seen in this cases, if we convert it to a bigger vessel also, they will move and they will cause partial pressure. So similarly, when we have taken in this containers also, they had different pressures, and we are taking them inside a same container. So when they are taken into the same container, how the pressures will be? That's what Dalton told us. So when they move and when they induce pressure, the pressure formed by the total of all of this will be equal to the sum of their individual pressures. So that's what Dalton told us. So the pressures induced by this three inside a bigger container will be equal to the sum of all the gases or the individual gases. So this had pressure P1, this had pressure P2, and this C had pressure P3. So when we transfer all of this to a same container, they will show a total pressure which is the sum of P1, P2 and P3. That's what Dalton told us. So the sum of the pressures of these three gases inside a same container will be equal to the sum of their individual pressures when they are separate in a separate containers. So P total, T means total, P total will be the sum of P1, P2 and P3. This is what Dalton told us. So the total pressure exerted by the mixture of non-reactive gases, that is very important. Once they are reacting, this might change. So the total pressure exerted by the mixture of non-reactive gases is equal to the sum of partial pressure of individual gases. So what is partial pressure? The pressure exerted by the individual gas in a mixture of gas is called partial pressure. So in this case, it is when we have this equation, P1, P2 and P3 are partial pressures of A, B and C. So that's what partial pressure means. And the Dalton law suggests us that the total pressure exerted by the mixture of non-reactive gases is equal to the sum of partial pressures of individual gases. This is Dalton's law of partial pressure, which can be represented by this. So P total is equal to P1 plus P2 plus P3, etc. How much ever gases we mix, all those sums will get us the P total. The constants are very important at constant temperature and the volume of gases. So usually when we find P total from a moisture condition, we do have another equation. So why is it needed? Because gases, when we collect, usually they are collected over water, even in the lab and in atmospheric conditions. So when we collect a gas, some amount of moisture will be present in the gas. So to avoid that error, we do have another equation. So pressure of dry gas can be calculated by subtracting vapor pressure of the water from the total pressure. So that's how we does that. So pressure exerted by saturated water vapor is called aqueous tension. And in the equation what we does is, when we want to find out the partial pressure of dry gas, we subtract the aqueous tension or the pressure exerted by saturated water vapor from the P total. So what we get? The partial pressure of dry gas. And if we don't do this, we get error in our calculations. So this is a contamination inside the gas. And removing the moist content from the dry gas is a very miserable process. So we don't do that. We just minus or subtract the aqueous tension from the P total to find out the partial pressure of our real dry gas. So that's all. Now we are moving on to the partial pressure in terms of mole fraction. I hope you all are clear with mole fraction in the first chapter. So mole fraction tells us the amount or the fraction of a single component from a mixture. So when number of particles of A is n, we divide it with number of particles of A plus B, or the total number of particles. For example, if a science exam was conducted in your school, out of 30 marks, and you got 7 marks for physics, 7 for chemistry and 8 for biology, and you want to find out the fraction of physics, chemistry and biology, what do you do? So you can divide it with the total sum, right? So 7 by 30 will be your fraction for chemistry and physics, and 8 by 30 will be your fraction for biology. So similarly, here also mole fraction does the same thing. Component A, number of moles of component A divided by total number will be the mole fraction of A. For B, it will be XA, which will be equal to number of particles of B divided by the total number. So this is what mole fraction represent, and we are applying this in partial pressures. So suppose at the temperature T, 3 gases enclosed in the volume V exert partial pressure P1, P2 and P3. So we are telling about partial pressure where T and V are constant. So in this case, when we substitute this into the equation, which is ideal gas equation, we get this equation. So we are rearranging the ideal gas equation and we get P1 is equal to N1 RT by V, P2 is equal to N2 RT by V, and P3 will be N3 RT by V. And we are combining these equations. So when P total becomes P1 plus P2 plus P3, so we have what is P1, P2 and P3. So we are substituting that. That becomes N1 RT by V plus N2 RT by V plus N3 RT by V. And we are taking this N1, N2, N3 and common. So we are getting this equation N1 plus N2 plus N3 into RT by V. So here we have got the equation for P total, and this we have to apply in mole fraction equation. So mole fraction, when we told we should divide one of the component with total. Same we are going to do that. Dividing P1, the equation of P1 by P total. There we get mole fraction. So we have found out the equation of P1 in this equation. So P1 is N1 RT by V. That we are going to substitute here. So P1, which is N1 RT by V, divided by N1 plus N2 plus N3 divided by RT, which is P total. So what we are doing? P1 by P total. Again, P1, one of the component divided by total. So hence we get the mole fraction of P1. I hope you are clear with that. You can pause the video and be clear with that, and we can move on. So we are dividing one component with the total. So we are getting the mole fraction of this component, P1 by P total. And this is the equation of P1 by P total. And when we rearrange the equation, we can take this upside. So this will become reciprocal, and hence rearranging the equation, we get this equation. P1 by P total is equal to N1 divided by N1 plus N2 plus N3 into RTV by RTV. We can cancel this 2 RTV and RTVs, hence we get this equation, N1 divided by N1 plus N2 plus N3, and this sum N1 plus N2 and N3, we can consider this to be N. So the total number N1 plus N2 plus N3 is equal to N, and hence the total equation becomes N1 by N. This is P1 by P total. So one component divided by total, which gives us X1. X1 is the mole fraction. So N1, N is equal to N1, N2, N3, the sum of N1, N2 and N3. Hence, one of the component divided by the total component gives us the mole fraction of P1. That's what the relation between partial pressure and mole fraction which we derived here. And in this equation, one more thing we can find out, which is, so P1 by P total is X1, right? P1 by P total is equal to X1. And if we want to find out the partial pressure of one component, what we can do? We can take this P total to this side. So it becomes partial pressure is equal to mole fraction into P total. This equation is very important because when we know the P total or the total pressure and the mole fraction, we can find out the partial pressure of any component. That's the importance of this equation. So when X1 is called the mole fraction of first gas, P1 is equal to X1 into P total. Hence P2 becomes X2 into P total and P3 becomes X3 into P total. So like this, any gas we can find out the partial pressure if we know the P total or the total pressure. So from this equation, the general equation can be written as Pi for gas I. Pi is equal to Xi into P total. That is the general equation. So as I told, this equation is very important when we know the total pressure and we want to find out the pressure exerted by individual gas. So that's about Dalton's law and about the relation between partial pressure and the mole fraction. That's all for today. Now you can prepare notes and be careful about solving the equations, and you need to be by-hearted very well. These equations will help you to solve a lot of questions in this chapter. Read the textbook thoroughly and prepare notes. Thank you.